Hello, class. Okay. So we're going to talk about the Doppler effect with regards to light. So mechanics 121, you learned about the Doppler effect with respect to sound waves. Now we're going to cover this for light. And in one sense, dealing with light is actually a lot easier than dealing with sound waves. The reason why, if you look at sound waves, well, let's talk about what the Doppler effect is, in case you forgot, but pretty sure everyone's seen it. So if you have a source of sound waves and an observer, and let's say like the source is moving towards the observer. So like, the source is producing sound waves, the observer is detecting them, and we can say the source is producing waves at a certain frequency. This is what you would hear if you were not moving with respect to the source. And like say you're both stationary. So got a speaker or like a tuning fork, say 1,000 hertz. What's the observer going to hear? And that depends, like if the source is moving towards the observer or the observer is moving towards the source. The reason why this is complicated when we're talking about sound waves is because there's actually 3 reference frames we have to consider here. One is the source, the other is the observer, and the third is the air, because this wave is traveling through the air. And so the result is you get different effects. Like say the source is moving to the observer with a speed of 100 meters per second. That will affect the frequency that the observer hears. On the other hand, if you have a stationary source, and say the observer is moving towards the source at 100 meters per second, you'll get different results. So, the source moving, observer moving, even though they have the same relative velocity with respect to each other, there's this third frame involved, which is air. And the source moving through the air is different than the observer moving through the air. So we ended up with a fairly complicated formula. Now, we're going to deal with a pretty simple case where we have relatively low velocity, but there's something fundamentally simpler in the sense when we're talking about light waves. There's something very unusual in that light moves the same speed with respect to everybody, which is something that is very shocking and hard to understand. So just to be clear what that means, let's say that we have a car driving by. Or here, let's say, we have a car. I guess it's a Volkswagen, because that's all I can draw. And say there's someone standing on the side of the road. And let's say this person on the ground throws a rock with a speed of 40 meters per second. So this rock is moving away from this person at a speed of 40 meters per second. Well, what about the car? How fast is it moving away from the car? Only 20 meters per second. So, it's just kind of these common sense notion about how things work. And that's actually kind of like the foundation of Newtonian mechanics. It is also, technically speaking, wrong. So let's look at a very similar problem. Now we have a car. I should draw a different car here. Let's say that's a horrible car. Not going to try. Try and draw a faster looking car. But let's say instead of throwing a rock, this person shines a flashlight. And we can look at one photon moving away from the person. And I'm writing this out to all its significant figures. Well, all of its figures, because by definition that is exact. Let me just double check. I always get these mixed up. Yeah, 299,792,458. Sometimes I think the 458 goes in the middle and 792 at the end, but yeah, that's the right answer. So this is the speed of the photon away from the person. Now you might think if the car is moving 20 meters per second, the speed of the photon relative to the car would be 299,792,438 meters per second. But that is wrong. The photon is moving away from the person at this speed. It's moving away from the car at the exact same speed. And that is very, very unusual. Like, that's just very strange and difficult to wrap your mind around. It'd be like you throw a rock and it's moving 40 meters per second away from the person, and here's this car. Let's actually make it even stranger. Let's say the car is going 39 meters per second. Now imagine if the rock was simultaneously moving 40 meters per second away from the person and 40 meters per second away from this car. That's going 39 meters per second relative to the person. That is very, very strange behavior. But that's actually how our universe works. Well, not in the case of the rock, but for light, that is exactly what happens. So if this car was going like, let's make a more comparable example. Let's say this car was going just a little bit slower than the speed of light. You might think he's catching up to this photon, or, approaching the speed of this photon. So like this photon's moving away from the person at this speed, and, or maybe a better example, say the car was at rest, it turned on its flashlights, and or the headlights, and you're looking at one photon moving away from the car. And then the car accelerates up to this speed, and you think he's catching up to the photon, but no, that photon is still moving the exact same speed away from the car. Whether he's at rest or moving in the direction of the photon, even if he's going almost the speed of light. And again, I'm not going to try to explain that. What's remarkable is Einstein actually thought of this before it was ever observed. Yeah, really amazing. This actually, he worked out in his mind where, Newtonian mechanics is based on some things that just are not true. That relate to like how we define time, things like that. Very interesting stuff. But basically, speed of light is the same for all observers. If you look at a beam of light, it's always moving the speed of light relative to you, regardless of what you are doing. Now, for our purposes, talking about the Doppler effect, that's actually an advantage because we can look at two cases. Like, say the source of light is moving towards you, or you move towards the source of light. It doesn't matter. There's only two reference frames to deal with here. And so we can write down a very simple formula. Now this is valid as long as, so let's define what these things are. FO, that's a frequency observed. Fs is the frequency of the source. V is the velocity, the relative velocity. Let's do that. So again, it doesn't matter if you're moving towards the source or the source is moving towards you. It's kind of the whole idea behind the principle of relativity is there is no difference. And c is the speed of light. And again, this only applies if the speed is significantly less than the speed of light. Okay, so that's kind of all we need to know as far as the Doppler effect. I'm not going to try to derive this, but I want to talk about what good is this. And it turns out this is extremely important, particularly in astronomy. The Doppler effect. Very, very important. So, Yeah, one thing we can do is, let's say we look at a star. We're seeing light from that star, and what if the star is moving towards us or away from us? We can tell if it's by observing the frequency, but there is kind of this fundamental problem. One is the frequency of the source. Like, say we're here on Earth, and we're looking at a different distant star. So there's light coming from the star towards us, and all we can measure is the frequency that we observe. We want to know if the relative velocity between us and the star, so we need to know the frequency of the source. So how do we know what that is? And amazingly, we can actually figure that out. And I want to just talk about this briefly because it's not something that we cover in this class. But let's take hydrogen, for instance. Since we're talking about astronomy, this is a good atom to consider. One, because it's the simplest atom, and two, 92 out of every atoms in the universe is hydrogen. So, if you're studying astronomy, you're mostly studying hydrogen. So we've got the nucleus, which is just a proton. And I mentioned that electrons can exist in certain orbits, and it can only have a stable orbit at certain distances from the nucleus. So let's say like this is the n equals 1 orbit, and this is the n equals 2 orbit. Alright, so the electron can exist here, or it can exist here. It can orbit at either of these two places, but it cannot orbit somewhere in between. And again, that's a very strange property of atoms. And like saying, you look at our planets, we have, the sun, and then the planets orbit at certain distances from the sun, but there's no reason you couldn't have something orbit anywhere else. We could put an artificial satellite in orbit between the Earth and Mars if we wanted to. But you cannot do that with atoms. So very different behavior. So anyways, the electron is going to have different energies depending on its orbit. It's going to have more energy here than it does here. Remember, this is a negative charge. It's attracted to the proton. If it could fall from this orbit to this one, it would accelerate. Just think classic physics. If you put a negative charge next to a positive charge, if it can move towards a positive charge, it's going to accelerate, gain kinetic energy. There is a stored potential energy in the atom. So it has more energy here than it does here. And, but it can't exist anywhere in between. So it's possible that an electron can jump from, say, the second orbit to the first orbit. Now, the question is, what happens to that energy? Say this electron jumped from this n equals 2 orbit to the n equals 1 orbit. It's going to give off energy. It has less energy here. And energy is conserved. That energy can't disappear. So what it's going to do is it's going to emit a photon. And let's say it has energy E1 here and energy E2 at that second orbit. The energy of this photon is just going to be that difference, whatever energy it lost as a result of jumping down in its orbit. So the point is, if you have this kind of thing happening in a hydrogen atom, where an electron jumps from this orbit to this orbit, it's going to give off a photon with a very particular energy. And one more thing that we don't cover in this class, this is something Einstein wrote about in his original paper on the photoelectric effect, but the energy of a photon is proportional to its frequency. And I'll write down one more thing. The speed of light is the frequency times wavelength. Okay. So if this electron jumps from n equals 2 to n equals 1, it's going to give off a photon with a particular energy, which means it has a particular frequency. And again, if you know the frequency, you know the wavelength. So maybe we're more familiar dealing with wavelengths. This photon has a very precise wavelength. And we could calculate that. We need to know this proportionality constant. You might have heard of it. It's something called Planck's constant. But let's just know that we can do this. We can actually find what the wavelength of this, this photon that it gives off is. And there's other possibilities as well. What if they jump from n equals 3 to n equals 1? Well, again, it would give off, that photon would have an energy of E3 minus E1. Or if it jumped from from the third orbit to the second orbit. So the point is there's particular photons that this hydrogen atom can emit. These are emission photons. It's giving off these photons, and there's only particular frequencies that it can give off, depending on these differences in energy levels. Now, I should point out, it's actually a little bit more complicated because there's other kinds of energy transitions that can occur in an atom. You know, you can think of the electron as like a ball that's spinning, like a ball of charge that's spinning, and so it has a magnetic moment, and that magnetic moment interacting with the nucleus has energy. So if it flips the way it's spinning, there's an energy transition as well. So it can give off photons. But let's just stick to these main jumps from one orbit to another. So anyways, if you look at a hydrogen atom, we can make a list of the photons that it can give off. Okay, now let's look at a different scenario. What about, like, how would it get to this n equals 2 state? You know, it can jump down because it loses energy in that process. So it can jump down and give off a photon. Can this electron jump up to a higher orbit? And the answer is yes, but it needs energy to do that. And, you know, where does that energy come from? Well, one way it could get that energy is to absorb a photon. However, that photon has to have the right amount of energy, which is this, E2 minus E1. So basically, if you hit it with a photon with this much energy, it can absorb that photon, and then the electron will jump up to the next level. And so this gives rise to a very interesting experiment. Actually, the experiment came long before this was understood. But say you have a source of light. So it's giving off light. And say we have a prism. Remember what happens if you shine light through a prism? That's something we're actually going to talk about later. But it creates a spectrum. It separates the, let's say it creates the spectrum here, where you've got all the colors of the rainbow here. So we can look at it in terms of colors, but you can also look at it in terms of it separating it by frequency or wavelength. And so, if you just have an ordinary light bulb and you shine light, you get this entire spectrum. Okay. Now the question is, what if we put, say, a hydrogen gas in between the light source and the prism? Now what happens is you get this whole spectrum here, except there are these lines. There's black lines where it's like, we're just not getting any photons at these particular regions in the spectrum. And again, these are particular wavelengths. There's certain wavelengths that are getting blocked by this hydrogen gas. And maybe you can guess it's these wavelengths that are causing these transitions in the atom. They're being absorbed by the atoms of hydrogen. And so the normal spectrum, it has every wavelength between these two extremes that we can see. we see the whole visible spectrum. So we're seeing all the wavelengths in between, except if we shine it through a hydrogen gas, they noticed that there were these dark lines. They're called absorption lines. And they had no idea why. And this model of the atom came about to explain what these absorption lines were. And so we looked at it just from this perspective because we know what atoms are, so we could do this. But back in the 1800s they did this. And they noticed these absorption lines. And again, they occur at very particular wavelengths. And again, that's a hydrogen gas. What if we change this to, say, nitrogen? Well, we'll get different lines. So basically, different wavelengths are being absorbed by nitrogen gas. And so scientists back in the 1800s started doing this. They just have all these different types of gases and record where these lines occur. And it's like each gas has its own like spectral fingerprint. It's unique to that gas. So if you shine an unknown gas, you can notice these absorption lines and say, okay, these are occurring here, here, and here. I've seen that before. That's nitrogen. Or that's hydrogen. And kind of a funny story. This was in the 1800s. There was a scientist in the 1800s, a little bit before these experiments came about, where he was talking about astronomy and the stars. He says, astronomers can study stars. We can determine where they are, how far away, how much energy they're giving off. When it comes to what these stars are made of, we're never going to know. Like, how could we possibly know? And he was proven wrong just a couple of years later. Because what they did is they did this experiment with sunlight, and they noticed, this rainbow with all these absorption lines. And they were able to say, okay, these lines here, those are hydrogen. These lines here are carbon, here's nitrogen. They noticed that the sun is made out of all the same things that we have on Earth. But they actually discovered a set of lines that they had never seen before. And so they realized that they had actually discovered an entirely new element. And, what do you do if you discover a new element? You give it a name. And because it was discovered in the sun, they decided to name it after a Greek sun god named Helios. So they called this new element helium. So kind of amazing. We never knew helium existed until we discovered it in the sun. And that was in the 1800s. I mean, they had no... just think of the limited technology they had in the 1800s. No photographs, they had no cameras, you couldn't take pictures. No real electronics at the time. And they were actually, even back then, they could actually figure out what the sun was made out of and even discover a new element in the sun. So, pretty amazing. Okay, so, just getting back to the Doppler effect. If you look at the light, you can run it through a prism. Something else we're going to talk about later, there's another way you can separate light by its frequency or wavelength, something called a diffraction grating, which would probably be more commonly used in these kinds of experiments. But you can look at these absorption lines and recognize these particular frequencies. Like you recognize like helium, it's supposed to have this, like we know what frequencies are absorbed, and so we can recognize these elements in the stars. And so that tells us, like, we'll know what the frequency of the source was. Just by looking at this spectrum, we have to look at, like, more detail, run it through and find out where these lines are, but then we can tell what the star is made out of and what the actual frequencies of the source are. And then we can compare that to what we see. Basically what happens, if you look at, like, hydrogen, you see this whole pattern of spectral lines get shifted by the Doppler effect. And so we know where these lines are supposed to be. Here's where they actually are. So we can determine these right here on Earth without actually being close to this distant star. And then from that, you can solve for the relative velocity. and discover the relative velocity between the Earth and, say, this distant object, like a star. I should also point out there's a plus or minus in the equation. I should have mentioned that. If the objects are getting closer together, the frequency would increase, and if the objects are moving farther apart, they would decrease. So you have to determine the plus or minus. Like if say the star is coming towards us, the frequency would decrease, so we would use the plus sign. If it's moving away, use the minus sign. Okay, so that is the Doppler effect. Very, very important in astronomy. And what's interesting is when they started studying, when they discovered galaxies, that was actually in the 1930s, so we really discovered galaxies. Now, we had seen galaxies before. You can even see the Andromeda galaxy without a telescope. So, obviously, we knew galaxies existed, but they didn't know what they were until the 1930s. So, less than 100 years ago, as far as we know, the entire universe was our galaxy. And as far as what these distant galaxies were, they thought maybe they were just things in our galaxy until they started measuring how far away they were. Not using the Doppler effect, there's other ways to determine the distance to an object. And we realized that these galaxies were basically like our own galaxy, just really, really far away. So the universe got a lot bigger in the 1930s. And it was the same person that discovered that, the same astronomer that discovered that distant galaxies existed. He also made another extremely important discovery. And that is that all the galaxies in the universe seem to be moving away from us. Andromeda is an exception, but mostly galaxies seem to all be moving away from us, which kind of raises the question, why? If you picture like a gas, things can be moving closer, farther away. Why is everything moving farther? And the reason is that the universe itself is expanding. So there's a really good analogy for that, like a one-dimensional analogy. Let's say we have a rubber band. And say we put let's say we put 3 dots on the rubber band. And now, what if we stretch the rubber band? So let's take that same rubber band and we stretch it. So just like these 2 points got a little bit farther apart. Now, these 2 points didn't actually move relative to the rubber band. They just got farther apart because the rubber band itself is expanding. So they got a little bit farther apart. But if you look at the extra distance between like here and the new location of this dot, this one grew a lot more. Like the distance between these two are close objects. They didn't move too much relative to each other, but this far away dot, that got a lot farther away. So this explains why, as our universe is constantly expanding, like everything is getting farther apart, and the farther away they are, the faster they're moving away from us. And because the distance between galaxies is so great, pretty much everything is moving away from us. Now, why is Andromeda actually getting closer to us? Well, Andromeda is very close to us on a universal scale. It's right next door. And Andromeda, like these dots are stationary, but imagine this dot is actually moving towards this one. And because the stretch didn't make these 2 dots move too far apart, the motion of like in this case, say this is Andromeda, the motion of Andromeda along the rubber band is greater than the rubber band stretch. So it's like the motion of Andromeda through space. It's moving through space faster than the space between us and Andromeda is growing. But again, that's only possible for objects that are very close to us. The farther away they are, the faster they're moving away from us. And so Yeah, it was the same guy that discovered both of these things. He discovered that galaxies exist outside of our Milky Way, and he discovered that the universe is expanding, and that was a huge discovery. It was something that was kind of almost predicted by Einstein when he came up with his theory of gravity in 1915. He kind of noticed that the universe could not be static. It had to either be expanding or contracting. But he didn't like that, so he modified his equations to give us a more static universe. And that turned out to be a mistake in a way that he could have predicted that the universe was actually expanding, but he didn't want to, so he didn't. But he wound up regretting that when it was proven or determined that the universe is actually expanding. And so, two enormous discoveries by one guy. Now, he thought this was one of the luckiest people alive. His name was Hubble. And he worked at the biggest observatory, the biggest telescope in the world at the time. It's called Mount Palomar. The Hale Telescope. It was at a mountain in California. And this was the biggest telescope at the time. And this was in the 1920s. There were no computers or remote viewing. If you want to look through a telescope, you are there looking through this. And, that was his job, to just look through this enormous telescope and see things no one had ever seen before. Or at least see in more detail than anyone had ever seen before. And he made these two great discoveries. And then he had a telescope named after him now, of course. We have the Hubble telescope. Yeah, very lucky guy. Okay, so I think that's enough on the Doppler effect. It's kind of more than we need for this class, but it's a very interesting subject, so went a little beyond what we needed to. But that'll be it for now.